Okay, so we're picking off in this buckling example where we already draw the column, right? So it's a square, 50 millimeters by 50 millimeters, and then we extrude it by 2.2 meters, right? So to do the buckle analysis, well, we do like any other analysis. We hit simulation and new study. So now over here now, we would normally do static, right? And then we use topology, but now we're going to use buckling here. So we hit buckling, click the arrow. So now we're in the buckling environment of this simulation. So again, we go through the normal procedure we did before. We apply our material. So in this case here, we're looking at 200 gigapascals. So you could remember we went through previously how to add your own custom materials. Right, so this is my custom material for normal mild steel. Right, so we have E is 200 gigapascals. Right, so based on the equation, we have seen that um, the critical buckling is only dependent material properties varies on E. So with that selected, next we go to fixtures. So we said that the bottom is fixed and the top is free to move. So we could fix the bottom here. Right, so that's our fixed boundary condition, and then the top is free to move. Right, so the top is where we have the load being applied. So external load, we right click and we apply a force on the top surface. Now with buckling analysis, finite element software would normally give you a factor of safety or a ratio of what your load is to the critical buckling load. Right, so if you put 100 newtons here, for example, it would give you, the solution would give you a ratio or a factor of what 100 newton is in terms of a factor of your critical load. Right, so to make things simple, we will just put 1 newton. So whatever factor we get will then be multiplied by 1, and that will give us our critical buckling load. Right, so we use 1 just to keep it simple. So that would be our load. Remember, a buckling analysis, critical buckling load is that we are just solving for that unstable load that will cause the unstable reaction of the beam. Alright, so mesh, create mesh. Again, everything is the same. You can make it a little finer if you want. Remember, based on your computer requirements, if you go too fine, it might actually might take too long. So the default is best. And then we could come and we could run or solve. Alright, so we have solved over here. Now, sorry about that. Alright, so I'm just trying to get the. Alright, so you can see the mode. The shape is the mode shape that we have been going accustomed to. Right, so this would be a cos type mode shape. Right, now if you look over here now, you would see top here, you would see the buckling amplitude 1, mode shape 1, because remember we said when n is equal to 1, you will have your first mode shape. Right, the load factor now is 53,148. That load factor is a factor of your critical buckling load to your applied load. And because our applied load was 1 Newton, well then this our buckling will be 53,148 according to according to SolidWorks. So if you were to look at our solution before, so if you go to your notes, you would see that our MATLAB script would have calculated PCR to be 53,104. And our SolidWorks give us 53,148. So we see we off by just you could say 44 newtons. Right, so that's the finite element software version result versus the analytical. So that is how we do a basic buckling analysis and determine your critical buckling loads in SolidWorks. Now this would be like a pre-analysis. Remember we spoke about pre-analysis. This would be a pre-analysis if you're doing a buckling calculation. So you would do a basic system first like this and verify it with your hand calculations. and we could tell that, okay, SolidWorks is giving us a reasonable value, and SolidWorks is calculating our buckling loads as we expect. So now whatever complicated system you have now, you could go now and build upon this. You could make a truss member here, right? You could change the diameter, the thickness. You know, we could make a complicated structure now and then use SolidWorks to determine the buckling load. And now we would have confidence knowing that, hey, it worked for the simple situation. Well, then the complicated situation, it's just a matter of more elements, more processing. But the answer, we could be confident to say that that is the correct critical buckling load.